Back to our quantitative methodology chapter. Now we're going to talk about the minimum sample size that you're going to need. So you'll notice this is quantitative, not qualitative. Quantitative means you're going to collect data and run a bunch of statistical analyses on those. So keep that in mind. Quantitative means statistical analyses. So let's get on with the show. So in your methodology chapter, you need to put in there what your minimum sample size was for your research, right? Are you going to use 10 people, 100 people, 1,000 people? Whatever the number is has to be in your methodology chapter, several times usually. And if you didn't know this, each statistical test that you have has a different minimum sample size. Important enough to say that again. Every stats test has its own different minimum sample size, just to ensure that the power is going to be good for the study, and we'll get to that here in a minute here. Sample size is very, very, very important in statistics because it's part of every calculation that I know of, and it does influence the results. And sample size is one of the very few things that you as the researcher can influence, right? You really can't influence power or effect size. The data will determine that for you. But sample size you can. And there's one of the rules in stats, the law of large numbers, bum, bum, bum. Basically, that means the bigger the sample size, the more believable the results. Just keep that in mind. Remember, you're always trying to prove that some information that you've gleaned from a sample can be generalizable to a population. And if you think about it, if your sample gets bigger and bigger and bigger, it will eventually reach the population. So whatever's true about your giant sample will be true for the giant population. Okay, just remember that. The bigger the sample size, the better. And I did just mention it a few frames earlier, but sample size is jointly related to the power of the study. So remember, the power of the study is the sensitivity of your statistical analysis to not reject the null when it's not supposed to and reject it when it's supposed to. So in other words, power is good. And let me give you a minor definition of power. I don't want to go into too much detail. This is not a power video, but we have power videos if you want to watch them. There is the calculation. That is the Greek letter, I believe it's iota. We don't use that anymore. But what that means is that the power equals, there's your little sample size right there, N. N is sample size. A capital N is the total number in a group or in a study. And a little n is the number in a specific group. But what this means is sample size times omega, that W thing, is actually the Greek letter omega, and that is an effect size, divided by 1 minus the effect size. So let me put that in English for you. Remember, effect size is the percent of the variance that you can explain. And down here on the bottom of this fraction, that's the percent of the variance that you can explain, which is what we call error or within group variance. So let's translate that into English real quick. But power is the product of sample size times your effect size divided by your within group error. Now, you can't do much for effect size, okay? The data is going to tell you what the effect size is after you run your tests. And it's also going to give you a within group error value there, but you really don't need to do that. But the only thing that you can control is sample size, right? Because it's the top of the fraction. When sample size increases, so does power. When effect size increases, so does power. But within group error, also called within group variance, when that goes up, power goes down, so you don't want that. So after you give them that number, your minimum sample size number, they're going to ask you this. How did you calculate that number? Some people just guess, right? They say, oh, 50 people is plenty. You can't do that. You need to show some kind of empirical proof on how you calculated your sample size. You have to show that to the IRB as well. So I'm going to run you through that real quick, and we're going to introduce you to G-Power. G-Power is a wonderful free program put out by the University of Dusseldorf. It's not exactly user-friendly. It does get a lot easier as time goes by, but it's an amazing free program. It does a lot, so thank you, Dusseldorf. Now I'm going to give you a quick $2 tour. Hold on a second. There's the icon. It's got the beta and the alpha and the two tables there, and this is what it looks like. I'm not going to rearrange the screen or something. I'll just kind of show it from the top. The latest version is 3.1.9.7. You're supposed to put that in for the IRB as well. They want to know what program, what version. That's us. It does a ton of stuff. So these are your test families. And let's just pick one. So F-test, that's your ANOVAs. And believe it or not, that's your regressions as well. So you pick one and you fill in the data. And you get a minimum sample size over here, right? Total sample size. And it gives you the actual power. And again, this is a priori. It means before you run the test. So don't overly worry about what the results are at this point in time. All right, back to the PowerPoint. Sorry, before we go back to the PowerPoint, I want to show you some resources for the G-Power software. So from the homepage of the Center for Student Excellence, that's the tutoring center, you scroll down there and you go, look at that, oh, G-Power. Da-da-da. You click on that. And it's got the link on where to get it. Get in there, you. Right? It's you got to download it. It's free. Everything's free. There's a manual. It's way over my head. I wouldn't even look at it, but it's there. And the good part is we got about a dozen of the most asked for G-Powers. So if you need to run a G-Power, there's a t-test, there's paired t-test, independent paired t-test, and one-way t-test. You got your ANOVA families, more ANOVAs. You got your man overboard. You got your correlations, you got your regressions, and I think there's even post-hoc analysis. Shows you how to do a post-hoc analysis on calculating your power after you run a test. So hopefully it will agree with what your power analysis was before you ran a test. Okay, so and there's all the gimmies right there. So I just thought I'd throw that in there. And very, very important, when we run that power analysis using G-Power, one of the things that you have to do is to pick an effect size. You get small, medium, or large. The software recommends a medium size, but what you're supposed to do is you're supposed to pick an effect size only for this a priori power analysis thing. You're supposed to pick an effect size that you read in a published research that's like yours. That's what your literature review should be going over. In a perfect world, somebody else would have run basically the same test that you did, and they would have come out with at least a medium effect size. And I'm about to show you why here in a second. But again, don't just pick an effect size. Don't take the one the software says. And it's always the middle of the road. It's called the Goldilocks zone. That would be great in a perfect world, but we're doing a different approach. They want you to follow in the footsteps of the other people. Now, this is an important warning, right? So let's pretend that you did find an effect size in some of the literature that you went over, and it was small. And you put a small effect size into the a priori G-Power, and it gave you a crazy sample size, which I'm going to go over here in a second. You just can't change the effect size on the a priori. That's not how it's done. Some teachers might catch you on it. They won't be happy about it, I guarantee you. But again, if your committee members are cool with it, then just run it the way they want it, because they're the ones that are going to be giving you the thumbs up or the thumbs down anyway, okay? So you got it. Don't just change the effect size because it gave you a crazy big sample size. This sample size big the same as your literature is what we call meta-analysis. Meta-analysis is a relatively new thing. I've been hearing about it for about 10 years now. But it's where they put these research studies together that have the same effect size. Say that again. Meta-analysis is where they tend to clump these analyses together based on their effect size being similar. So I've been warning you about a small effect size going to do strange things to your sample size. I'm going to show you, okay? So let's do an actual example. Hold on. So forgive me, I'm just going to use the good part of the screen here for the G-Power. It goes up and it goes down, but this is the guts of it right here. So let's just pretend we're going to run an a priori power analysis to determine the minimum sample size needed for an independent t-test. So you go to your test family. We're just going to stick in the t-test. And then we go over here, and it says what kind of t-test. And we want to look at independent differences, right? So means difference to independent means. Boom. And we're just going to leave it as a one-tail. We expect one side to be bigger than the other side or have greater depression scores, whatever it is, right? And you see that? It gave you an effect size. That is suggested, and that's a medium. That's a Cohen's d. So Cohen's d of 0.50 is considered a medium effect size. We get the change, okay, the critical alpha, we just leave it at 0.05. But we get the change at power down to 0.80, just 0.8, because we're a social science. And we expect the sample sizes to be relatively the same. Now down here off the bottom that you can't see is a calculate button. And I'm going to calculate it. So according to the G-power, we need a minimum sample size of 102. You know, and again, in a perfect world, we'd have 51 in each group, but they're never the same size. So, but again, we need at least 102 people to get the power of 0.80, right? That's the whole thing. Now, watch what happens when I change this effect size to a small effect size, which is 0.2, which is 0.2 is considered a small effect size. And I hate to say this, but most of the articles that I've read, they have a small effect size. So remember, with a medium effect size, it was 102, but with a small effect size, it jumped up to 620. So keep reading. So if you can't find an article with a medium effect size, keep reading or change the test you're going to use, okay? Again, a small effect size skyrockets your sample size, and that's true for all of your tests. And again, only for this a priori stuff. So I know I've beaten you up pretty bad about that a priori stuff. Now, here comes the good news is you could get an a priori power analysis statement that says, oh, you need 102 people to run this t-test, right? Now, that is a guide. It's not carved in stone. You can still have a smaller sample size. The difference could still be significant. Whatever you're looking for could still be significant. And your power could still be greater than 0.8, and you could have a medium to large effect size. That is possible. It depends on if the difference is in fact there. It will show significance and strong power and good effect size with a much smaller sample size. All right, moving on. So some teachers want you to justify, why did you use a power of 0.8? Why didn't you use 0.9? Why don't you use 100? Okay. We always give the same answers, right? The social science, that's what the other people call the soft science, because what we're trying to measure is difficult to measure. We always measure things with surveys, right? We don't have a ruler. We're not cutting wood where we can get an exact measurement. We're using surveys. And as we all know, people can not be truthful or be easily misunderstood. So that's why we get to cut the power down to 0.80. And the bottom line is that the sample size is very, 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 I could have put in 100 berries. Just remember, sample size is very important to statistics in general. Just keep that in mind, right? The bigger the sample size, the better. And I think we're running down out of time here. Let's see what we got. Dun, 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 dun. Yep, that's it. All right, I hope this helps. And get out there and run your a priori power analysis. Get that minimum sample size. All right, that's it.
Math Guy Zero.